to configure the OCI. Hello and welcome to this demo on deploying a fully functional WordPress site using OCI container instances. I am Mahendra Mehra, Senior OCI Instructor with Oracle University. In this demo, we will take a close look at how to get started with the container instances service and its various controls to quickly and easily launch and manage container workloads on Oracle Cloud Infrastructure. We shall create a fully functional WordPress site by running both the WordPress container as well as MySQL container in the container instance service. The WordPress site image will be pulled from the third-party container registry, which is Docker Hub, while the MySQL container image is hosted on the OCI container registry, also known as OCIR. So let's get started. I've signed in to my Oracle Cloud account and this is my OCI console. The first task is to create and configure a container instance. I'll click on the hamburger menu and click on the developer services. Under containers and artifacts, I'll click on container instances. This opens up the container instances service page. Under the compartment section, I will ensure to choose the right compartment where I wish to create my container instances. And in my case, it is CTD OKE compartment. I will now click on the Create Container Instance button. This opens up the container instance creation wizard. And the first step is to add basic details for our container instance. Let's give our container instance a suitable name. I'll remove the timestamp here and just give it a suffix as demo. I'll make sure that the right compartment is selected for the container instance creation, which is CTD OKE. The placement options include the availability domain you would like to place the container instance in, and as well as the option to choose a fault domain of your choice. I'll go ahead with the default selection, which is availability domain 1. And if you wish to select your fault domain, you must click on Show Advanced Options. Under the fault domain options, you can select the fault domain of your choice, or you can let Oracle choose the best fault domain for you. I'll select the first option, which is let Oracle choose the best fault domain. Moving on, we have to choose the shape. Basically, a shape is a template that determines the number of CPUs, amount of memory, and other resources allocated to an instance. By default, the shape selection is CI standard E4 Flex with 1 OCPU and 16 GB memory. However, you can customize this shape by choosing from various options available. To see the various other options available, we'll click on Change Shape button. This opens up Browse All Shapes window where multiple options are presented. This includes AMD, Ampere, and other shapes. As I mentioned, the default selection is AMD CI standard E4 Flex. You can opt for ARM-based processor where the option is CI standard A1 Flex, and under More Shape options, you have the option to select CI standard E3 Flex. All of these shapes are flex shapes, allowing easy customization of OCPUs and memory for your containerized workloads. For example, if I select ARM-based processor, where I have the option to select CI standard A1 Flex shape, I can change the number of OCPUs from 1 to 16, and based on which the amount of memory will also change. Additionally, there is an option for extended OCPU. When the number of OCPU is set beyond the standard limits, the instance becomes an extended OCPU instance. The standard limit for ARM-based processor is 1 to 16 OCPUs, but if we extend the number of OCPUs beyond 16, it becomes an extended OCPU-based instance. Remember, although container instances with extended OCPUs may take longer to create, they are beneficial for high-demand workloads requiring more cores than standard limits. And remember, the extended OCPU option is available under all shape series. If I select AMD, the default range or the standard limit is 1 to 8 OCPUs, but if we extend the OCPUs beyond 8, it becomes an extended OCPU. For this demo, I'll be selecting ARM-based processor and change the number of OCPUs to 4. And the amount of memory, as you can notice, has been adjusted to 24, as for each OCPU you can select up to 6 GB of memory. You also have an option to downgrade the amount of memory if you don't want the automatically adjusted value. Let's say I select 12 over here. I'll click on select shape, and as you can notice, the shape information has been updated. We are using CI standard A1 flex with 4 OCPU and 12 GB memory. Next, we have to define the networking configuration. This lets you choose the networking options like VCN and subnet you want your container instances to be on. You have the option to select existing virtual cloud network, or you can create a new VCN on the fly, or enter the subnet OSIT for an existing subnet. In our case, I already have a VCN created which I'll be reusing, which is CI demo. Under the subnet, I'll select the existing subnet, which is a public subnet. And if you wish to access your container instances using public IPv4 address, we must select the assign a public IPv4 address option. Under show advanced options, we have different tabs. Under the advanced options, you can select the use network security groups to control traffic going in and out of your container instances. You also have an option to enable source destination check. By default, every VNIC performs the source destination check on its network traffic. The VNIC looks at the source and destination listed in the header of each network packet, and if the VNIC is not the source or destination, then the packet is dropped. You can also provide your private IPv4 address and set up DNS records. You can also assign a host name for your container instance, but these are all optional. For now, I won't be using any of these, so I will click on Hide Advanced Options. And under the Show Advanced Options at the container level, you have the option to specify the graceful shutdown timeout in seconds. This is the time given to the containers within a container instance to gracefully exit when the container instance is terminated. I'll set it to 30 seconds. You can also set a container restart policy to automatically restart containers that exit or terminate, or base the restart policy on the exit status of the container. For example, if I select on failure, so whenever my container fails in the container instance, it will try to restart the containers. I will now click on next. We have covered a lot in this session, but to keep things focused, we will continue exploring in the next video. So stay tuned, and I'll see you in the next video. Welcome back. Let's continue from where we left off in our last session. Now it's time to define the first container in the container configuration section. In this example, as I mentioned, we will start with the WordPress container. So I will name the container as WordPress. In the image section, we'll have to select the image. Like I said, you get two options to select the image from. If I click on Select Image button, I have two options. One is OCI Container Registry and the other one is External Registry. So for the WordPress site, we will be using an external registry, and we'll be pulling the official WordPress image from the Docker Hub. So I'll provide the registry hostname, which is docker.io, and the repository name is WordPress. Here specifying the image tag is optional and it defaults to the latest. So in our case, it will pull the latest WordPress image from the Docker Hub. Under the registry credentials type, the default option selected is none. But if your registry or repository you're using is private and requires authorization in order to pull the images, you have two choices. One is basic authentication or OCI Vault Secret. With basic authentication, you just put your credentials in the username and registry password fields. And with the OCI Vault secret, you first save your credentials in the OCI Vault service and then use them for authentication. But remember that OCI Container Instance Service must have permissions to read the Vault secrets provided for image authorization. I've already covered the IAM policies required for container instances in the previous lesson. You can either create the secret using the OCI Vault service and select the secret from the options available here. Since we don't have a secret already created, you can also select the create new secret and create the secret on the fly. This opens up the create secret window, and here you need to just specify the name of your secret, give it a description, select the master encryption key that you'll be using to encrypt your secret, and provide your registry username and password in the fields given. Once you click on create secret, the secret is created, and that secret is used for authorization to pull the image from the private repository or registry. In our case, the WordPress image that we are using for this demo is available as public image in the Docker Hub repository, so we won't be needing to create a secret. I'll click on cancel here and go back to the first option, which is none, and click on select image. Now let us set some environmental variables to use this WordPress image, and this information is available in the official documentation for the image on the Docker Hub. I'll start creating environmental variables. The first variable is WordPress_db_host, and the value is 127.0.0.1. I'll click on add another variable, and now it's time to add WordPress DB user. The value I'll specify is WordPress. I'll click on add another variable to add the password, which is WordPress_db_password, and provide the value as WordPress. Click on add another variable and add the DB name, which is WordPress_db_name, and name RDB as WordPress. So with this, I've set up the environmental variable required to set up our container instance running WordPress image. Also remember, when you have multiple containers within a container instances, just like in our case, we have one WordPress container and we'll be creating another MySQL container. They will share the same compute resources like CPU and memory that are available to the container instance. In our case, it's 4 CPU and 12 GB memory. Also, they share the same networking namespace, which is why the WordPress container can connect to the MySQL container over localhost or the loopback address, which is 127.0.0.1, as we have configured in our environmental variable. Now let's look at some of the advanced options. I'll click on show advanced options. Under the resources tab, you have an option to restrict the amount of resources that the container consumes. And remember, by default, the container can use all resources in the container instance. So to avoid one container from utilizing too much of these resources and starving other containers in the container instance, we can throttle the resources made available to each container by selecting enable resource throttling option. I'll select the percentage option and throttle the value of vCPUs and memories to 50% for this container, which means the WordPress container will only be able to use 2 OCPUs out of the 4 OCPUs that we have allotted to this container instance, and also limit the memory size to 6 GB out of the total 12 GB that we had allocated to the container instance. Under startup options, you have the option to override some image defaults like the working directory, the command, and the command arguments. And these options are available for each container under the advanced options. For WordPress site, we won't be changing any of these details. On the security tab, you can enable or specify security settings of the container. If you check the enable read-only root file system, This will apply read-only access to the root file system of the container. If you check run as non-root user, this will ensure that the root user doesn't run the container. When you enable run as non-root user, the user ID value cannot be 0. It must be a number between 1 to 65535. And if I uncheck this, you can use the user ID and group ID combination to run the entry point process of the container. The value for user ID and group ID must be an integer between 0 to 65535. And if no value is specified, the default value is 0, which stands for root user. Only once you set the user ID field, the group ID field gets active and you get to specify the group ID. Under Configure Linux Capabilities section, you can configure Linux capabilities for your container. By default, the container launches with several capabilities that you can choose to drop. Both Add Capabilities field and Drop Capabilities field support all value, which allows to drop all capabilities or add all capabilities that are enabled by default. And if you leave both the add capabilities and drop capabilities blank, all default capabilities are available for your container. If you enter all in the add capabilities field, all capabilities are available except those that you list in the drop capabilities field, and ignores all in the drop capabilities field. And if you enter all in the drop capabilities field, the container contains only capabilities that you list in the add capabilities field. For this demo, I won't be needing these features or capabilities, so I'll remove them and would want my container instance to run as root, so I'll remove the user ID and group ID. With this, we've completed setting up the container values for our WordPress container. Now we'll go ahead and create another container by clicking on Add Container button over here. We have covered a lot in this session, but to keep things focused, we will continue exploring in the next video. So stay tuned and I'll see you in the next video. Welcome back. Let's continue from where we left off in our last session. Now our WordPress also requires a database to function. And in this demo, we shall run a MySQL database as a second container within the container instance. Let's give this container a suitable name. I'll click on Select Image. In the interest of time, I have already pulled a MySQL image and hosted it on the Oracle Cloud Infrastructure Registry. I will quickly go ahead and show it to you. I'll duplicate this tab and click on the hamburger menu, go to Developer Services and click on Container Registry. Now under my CTD OKE compartment, if I click on the drop down for repositories and images, you can notice I have a MySQL repository which is public, and there's an MySQL image hosted on it with the tag 8.0.31. Now I'll switch back to the previous tab, and here I'll select the first option, that is specify an image from an Oracle Cloud Infrastructure Registry, which is OCIR. I'll select the repository name, which is MySQL, and also select the image in the repository. The only image that's available there is 8.0.31. I'll click on Select Image. As you can see, it rightly reflects that it's pulling an image from OCI Container Registry, and this is the path to the image. Now I'll go ahead and set up some environmental variables to initialize the database. The first variable that I'll be setting up is MySQL root password, and the value is WordPress. I'll click on Add another variable, and I'll set up the MySQL database, which again is WordPress. Now I'll go ahead and set up MySQL user using the key MySQL_user, and for the sake of simplicity, I'll give it the value WordPress. Click on Add another variable and set up the MySQL password. and again provide the value as WordPress. I'll go ahead and click on show advanced options, and similar to the WordPress container, I will be enabling throttling for this container too. I'll click on enable resource throttling, select the percentage option and set the throttling to 50% both for CPU as well as memory. So which means out of the 4 OCPUs that I had configured for this container instance, 2 will be used by WordPress container and 2 OCPUs will be used by MySQL container. And likewise for the memory, out of the total 12 GB memory that I had reserved, 6 GB will be used by WordPress and 6 will be used by MySQL. Under the startup option, I will set up the parameter to override MySQL container's entry point argument. So in the command arguments field, I will set up the value as this plugin called MySQL native password is a traditional authentication method used by MySQL servers to authenticate users. When this flag is set, MySQL will accept clients to provide passwords in the hashed format accepted by MySQL native password plugin during the authentication. This flag ensures compatibility with older MySQL clients and applications that accept this authentication mechanism. Remember, MySQL native password authentication plugin is not recommended in production environment. We have more secure and better alternatives that are available. Now I will click on next and review all the information. I will just cross-check all the information that we had configured to create these container instances. So as you can see, the name of our container instance is container instance demo. It's using the CI standard A1 flex shape. The availability domain is phx81. Under networking section, we can confirm that it's using an existing virtual cloud network, which is container instance demo, CI demo, and it will be assigned a public IPv4 address. Container 1 is WordPress container, which will pull the image from Docker Hub with the following environmental variables. And container 2 is MySQL container, which will pull the container image from OCIR repository as mentioned here. And these are the environmental variables with which it will be configured. Everything seems to be good. Let's go ahead and click on create. Well, as you can notice, the container instance is in creating state, and within a few seconds, the workloads will be live. Let's scroll down. As you can notice, the container instance creation process is in progress. In the meanwhile, I'll click on containers. And we can observe that there are 2 containers getting created. And like I said, since we have enabled resource throttling, the CPU utilization limit for each of them is set to 2 OCPUs, 2 for MySQL container and 2 for WordPress container, as well as the memory limit is restricted to 6 GB per container out of the total 12 GB that was allocated to our container instance. Alright, our workload is now live, and since we chose to assign a public IP address to the container instance, we can use that to reach our WordPress site on the internet. I'll copy the public IP address. Now, one important thing to note here is that the ports that your applications listen on need to be allowed on the subnet security list or the network security group for an instance to be able to receive a connection. In our case, I've already configured the security list for the existing VCN that we are using, that is CI-demo. Let me go ahead and show it to you. I'll click on the subnet link and open it in a new tab. I'll click on the default security list for the VCN. Now, since our WordPress site is listening on port 80, I've configured the ingress rule to listen on port 80. If you notice, I have set up a rule to allow all incoming traffic on port 80. and this is essential for us to access the WordPress site using the public IPv4 address. Okay, I'll go back to the container instances page and copy the public IP address once again. I'll open up a new tab and try to hit the public IPv4 address. I'll go ahead and hit enter. Now, as you can see, our WordPress is live on the internet. Let me go ahead and do some quick installation process. I'll go ahead with the default language selection, which is English. Click on continue. Provide a suitable name for the site title. Let's say CI demo. Give it a username, which is provide a username for our WordPress installation. The password is auto-generated, so I will leave it to the same. Let's enter the email address. I'll copy the password and click on install WordPress. Now the WordPress has been installed successfully. I'll click on the login link to log into the WordPress site and use the saved credentials to log in. And there you go. With this, we confirm that the WordPress is live and the installation was successful. With this, we come to the end of this demo where we saw how to deploy a fully functional WordPress site using OCI Container Instances service. I hope you enjoyed the demo. See you in the next one. Thank you for watching. Hello and welcome to this demo on working with container instances. I am Mahendra Mehra, your senior OCI instructor with Oracle University. In this demo, we will cover basic administration tasks and learn how to monitor the health, capacity, and performance of your OCI container instances. Let's jump in. I've already logged into my OCI console and this is my OCI dashboard. I'll click on the hamburger menu and go to the developer services, where I'll click on container instances. And from the list of container instances, I'll select the one that we created in our earlier demo. Well, as part of administration, you can either edit the existing container instance info, that is, you can change your container instance name. You can stop your container instances, you can restart them, or you can start the already stopped container instances. Under More Actions drop-down, you get an option to edit your VNIC. You can move your container instance resources from one compartment to another. You can add tags to your container instances, or you can delete the container instance. Under the Resources section within the Metrics tab, you can monitor the health, capacity, and performance of your OCI container instances. You can filter metrics based on start time and end time range, or you can use the quick select options. Choose any of the options from the drop down. You can view the CPU utilization metric, which gives you the % of container instances CPU resources that are in use. You can also view memory utilization, that specifies the % of container instances memory resources that are in use. Under CPU used metrics, you get the cumulative use of the container instances CPU resources since it was created. And similarly for memory used, you get the information on the amount of container instances memory resources that are in use. And towards the end, you get to see the ephemeral storage used. This is the amount of container instances ephemeral storage that is in use. Now, to get more detailed information about containers running within your container instance, you must select the containers link under the resources section. And here it lists you the containers that are created within your container instance. We had created 2 containers as part of our earlier demonstration. We have the WordPress container and the MySQL container running within this container instance. To get more detail about specific container, you must select the container from the list. I'll select the MySQL container. Here you get options to edit the name of your container. You can also view the entry point arguments that were set up at the time of container creation. In this case, we had set up the default authentication plugin to MySQL native password. You can also view any commands that were set at the time of container creation that overrides the command within the container image. In our case, there is no command that was set for this container. You can view the environmental variables that were set at the time of container creation. We had set up some environmental variables which are visible here. I'll click on close. And if you want to view logs of your containers, you must click on view logs button. This opens up a window where you get to see the logs of your MySQL container. So in case you need to troubleshoot your container, you can always come and look at the logs. That will help you troubleshoot your container issues. You can periodically click on the refresh button to view the updated logs. I'll click on close here. And if you want to take a look at the metrics of your particular container, you can scroll down and look at the metrics such as container CPU used and container memory used. Also the container ephemeral storage used. These metrics are particular to the MySQL container. I'll go back to the container instance page. And like I mentioned earlier, you can click on the stop button to stop your container instance. But remember, it will first stop all the containers gracefully, and that depends upon the graceful timeout specified at the time of container creation. And if the containers take more time to stop than the graceful timeout allows, they are terminated by the container instance service, and any ephemeral data hosted by those containers will be lost. Remember, the billing depends on the shape that you use to create the container instance, and container instance use standard shapes which pause billing when a container instance stops. However, stopped and failed container instances continue to count towards your service limits. And before we wrap up, there's one more critical point to highlight. It's essential to note that the creation of your container instances may fail if the container image's architecture mismatches with the shape chosen for the deployment. So keep in mind that you cross-check the container image's architecture is compatible with the shape that you have chosen for the container instances. This will ensure a smooth deployment process. Thanks for joining us on this journey into container instances. I hope you enjoyed the demo. See you in the next one. Thank you for watching. Hello and welcome to this module on Kubernetes Basics. In this module, we'll cover the fundamentals of Kubernetes, the leading container orchestration platform. In this module, we'll cover the Kubernetes architecture, its main components and features to give you a solid foundation on understanding how Kubernetes operates. Through hands-on demonstration, we will be covering some Kubernetes basic commands that enables you to interact with Kubernetes clusters effectively. So let's get started. Hello and welcome to this lesson on Introduction to Kubernetes. My name is Mahendra Mehra and I am a Senior Training Lead and Evangelist with Oracle University. So, you've heard of Kubernetes, but you don't know what it is, or you've been playing with Docker and containers and you want to know how to take it to the next level. In this lesson, we are going to take a look at what Kubernetes is and see when and where we might want to use it. So let's get started. While deploying and managing microservices in a distributed environment, you may run into following issues. Issues such as failures or container crashes. Issues such as scheduling containers to specific machine depending upon the configuration. You also might face issues while upgrading or rolling back the applications which you have containerized. Scaling up or scaling down containers across a set of machines can be troublesome. Meet Jamal. Jamal loves working with containers. A container is a standard unit of software that packages up codes and all its dependencies so the application runs quickly and reliably from one computing environment to another. Think of them as lightweight virtual machines. He designs his applications using containers and sees that it's working great. So Jamal then gives a go ahead to Trisha from operations to deploy the application in the production servers. The application becomes popular over time, and now to keep up with the increasing demand and to manage the growing workload, Trisha needs to scale her resources. Now instead of a handful, she has to deal with hundreds of containers. Trisha is overwhelmed. She needs a simple way to automate the entire process. This is where Mo comes in and introduces Trisha to Kubernetes. So, what is Kubernetes? Kubernetes is a portable, extensible, open source platform for managing containerized workloads and services that facilitates both declarative configuration and automation. Well, if the definition isn't clear to you, here's an analogy. You can think of a Kubernetes as you would a conductor for an orchestra. Similar to how a conductor would say how many violins are needed, which one play first, and how loud each should play, Kubernetes would say how many web server front-end containers or back-end database containers are needed, what they serve, and how many resources are to be dedicated to each one. In Kubernetes, there is a master node and there are multiple worker nodes. Each worker node can handle multiple pods. Pods are just a bunch of containers clustered together as a working unit. So Trisha starts designing her application using pods. Once Trisha has her pods ready, she tells the master node the pod definitions and how many she wants to be deployed within the desired state. For example, Trisha here wants to deploy 3 containers having microservice A and 2 containers of microservice B and C each. From that point, Kubernetes is in control. It takes the pods and deploys them to the worker nodes as per their availability and load status. Let's say if a worker node goes down, Kubernetes starts new pods on the functioning worker node. Trisha doesn't have to worry about complexity of managing containers anymore. She can spend time on observability and managing security of the application. Trisha is happy to see the end results. So in a nutshell, Kubernetes can containerize application of any scale without any downtime. Kubernetes can self-heal containerized applications, making them resilient to unexpected failures. Kubernetes can auto-scale containerized applications as per the workload and ensure optimal utilization of cloud resources. Kubernetes also greatly simplifies the process of deployment operations. With Kubernetes, however complex an operation is, it could be performed reliably by executing a couple of commands at the most. To wrap up, we discussed challenges in containerizing application within complex business setup and understood how Kubernetes facilitates container orchestration and improve its effectiveness, which results in better software performance, flexibility, and availability. I hope you liked the lesson. See you in the next one. Thanks for watching. Hello and welcome to this lesson on Kubernetes architecture and main components. I am Mahendra. Welcome back. Let's continue our exploration from where we left off in the previous video. Now, to fully utilize the OCI native ingress controller, you need to create several Kubernetes resources. Here's a breakdown of each resource. First one is the ingress class parameter resource. This custom resource defines the specifics of the OCI load balancer that the OCI native ingress controller will create. Next is the ingress class resource. This resource is responsible for creating a new load balancer. This ingress class resource will reference the ingress class parameters resource to determine the characteristics of the load balancers to create. It also specifies whether the OCI native ingress controller should be the default controller for ingress resources. Let's head back to our local machine and take a look at the service manifest for these resources. I'll move to the directory where I have these resources created. Let's take a look at our manifest where we have defined both the ingress class parameter resource as well as the ingress class resource. This manifest has two distinct sections separated by 3 hyphens. In the first section, we'll define the ingress class parameters. Let's break down the components of ingress class parameters resource. The API version specifies the version of ingress class parameter resource, and it indicates that we are using the ingress.oraclecloud.com/v1 beta 1. Kind ingress class parameter declares that we are creating an ingress class parameter resource, and the ingress class parameter is a custom resource defined for configuring parameters related to the OCI load balancers within Kubernetes cluster. Metadata section contains information about the ingress class parameter resource, such as its name, which is ingress params-cr-test, and the namespace indicates the namespace in which the resource is located. In our case, it is test. Specs section defines the specifications or configuration parameters for the ingress class parameter resource. Starting with compartment ID, this specifies the OCID of the compartment where the OCI load balancer will be created. And in our case, this is the CTD-OKE compartment's OCID. The subnet ID specifies the OCID of the subnet where the load balancer will be provisioned. Load balancer name specifies the name of the load balancer that will be created within OCI, and in our case, it's native ICLB. Is private set to false indicates whether the load balancer should be private or public. In this case, it is set to false, meaning the load balancer is public. Max bandwidth Mbps and min bandwidth Mbps. These parameters specify the maximum and minimum bandwidth, respectively, for the load balancer measured in megabits per second. The load balancer's bandwidth determines its capacity to handle incoming network traffic. In this case, the max is set to 400 Mbps and the min is set to 100 Mbps. The next section defines the components of our ingress class resource. Let's break down the component. API version indicates the Kubernetes API version used for the ingress class resource, and in this case, it's networking.k8s.io/v1. The kind specifies that we are creating an ingress class resource which is used to define the ingress controllers. Metadata section contains information about the ingress class resource. Under the name field, we have defined the name of the ingress class, which is default ingress class. Annotations are additional metadata associated with the resource, and this annotation here marks the ingress class as the default one. It means if no specific ingress class is specified in an ingress resource, this one will be used. Spec section defines the specification or configuration parameters for the ingress class resource. Here the controller is set to oci.oraclecloud.com/native ingress controller. This specifies the controller responsible for managing this ingress class. Parameters specifies additional parameters for the controller, where under the scope field we specify that this controller is limited to a namespace and the namespace is set to test. API group field specifies the API group for the controller, indicating the resources it manages. Kind field specifies the kind of parameters expected by the controller, which is set to ingress class parameters. And the name field here specifies the name of ingress class parameter resource associated with the ingress class. It indicates the configuration parameters for the OCI native ingress controller, which we had specified in the definition of our ingress class parameters resource. I'll close this file. Now I'll run the kubectl apply command and run the manifest within our Kubernetes cluster to create the ingress class parameter resource as well as the ingress class. I'll hit enter, and from the output it's confirmed that our ingress class parameters resource has been created as well as our ingress class resource with the name default ingress class created. Now once we create the ingress class parameters and the ingress class resource, the next step is to create the ingress resources. This resource defines the rules to direct the external traffic to the backend services. Let's head back to the local machine and see this in action. I already have an Nginx deployment with the respective Nginx service referring to the deployment. I'll first apply the deployment manifest and the service manifest to the Kubernetes cluster. Well, this will create an Nginx deployment and an Nginx service within our Kubernetes cluster. I'll go ahead and hit enter. Well, if you notice, a deployment name Mahindra deployment and a service name Nginx service has been created. I'll run the kubectl getAll command. And as you can notice, our deployment is running 3 pods with the service Nginx service of cluster IP, which is active. Now I'll open up the ingress resource that I've created for this Nginx deployment. Now this YAML manifest defines an ingress resource in Kubernetes. Let's break down its components. The API version indicates the Kubernetes API version used for the ingress resource, and in this case it's networking.kh.io/v1. The kind has been set to ingress, which specifies that we are creating an ingress resource. Metadata section contains information about the ingress resource, where we have specified the name for this ingress resource, which is native IC ingress Nginx. Spec section defines the specification or configuration parameters for the ingress resource. The first parameter under the spec section is the ingress class name. This specifies the class of the ingress controller that should be used to implement the ingress. And this refers to the name of the ingress class resource we created a while back. Rules defines the routing rules for the incoming traffic. Here HTTP indicates rules apply to HTTP traffic. Paths specifies the path for which the rule applies. The path type has been set to exact. This specifies that the path matching should be exact, and the path field value is set to /. This specifies that the exact path / for which this rule applies. And backend specifies the backend service to which the traffic should be forwarded if the path matches. Service specifies the Kubernetes service to which the traffic should be routed. Name specifies the name of the backend service, which in our case is Nginx service, which we created a while ago. Port here specifies the port on which the service is listening, and in our case, the Nginx service is listening on port number 80. This indicates that the traffic will be forwarded to port 80 of our backend service Nginx service. I'll close this manifest and use the kubectl apply command to apply this to our Kubernetes cluster. Well, the output confirms that the ingress resource has been created with the name native IC ingress Nginx. Now I'll run the kubectl get ingress command to get the load balancer's IP. From the output, we can confirm that we have an ingress resource created with the name native IC ingress Nginx, and the ingress class that it is referring to is default ingress class, created in the default namespace of our Kubernetes cluster. And this is the IP address of the load balancer that the ingress created for us. I'll copy the IP address. I hope you're liking this video so far. See you in the next one. Thank you for watching. Welcome back. Let's continue our exploration from where we left off in the previous video. Now I'll move to the OCI console and I'll show you the load balancer that got created as part of our demonstration. I'll go to the load balancer service, click on networking, click on load balancers. Here I'll click on load balancer, and as you can notice, we have our load balancer with the name native ICLB created with the IP address available in the IP address column and the overall health of which says OK. Now if I select this load balancer and go to the backend sets, You can notice that there is a backend set created for this load balancer. Now this backend is derived from the Nginx deployment that we are running in our Kubernetes cluster. And since the replica set count has been set to 3, there are 3 backends available as part of this backend set. If I click on the backends, you can notice that these are the 3 pods that are running our Nginx deployment. Just make a note of the IP address, and if I go back to the local machine, I'll clear the screen here and run the kubectl get pods -o wide command. Well, these are the 3 pods running our Nginx server, and they are all running on the node with different IPs, but the pod IPs are mentioned here, and these pod IPs is what we see in the backend set for our load balancer. This means that the traffic coming to the load balancer will be diverted to these pods. If I go back to the backend sets, the other one is the default ingress backend, which I have not defined. That is why it says incomplete. We can also define a default ingress to specify the default backend to which the traffic must be directed. Now I'll open up a new tab and paste the load balancer's IP over here and hit enter. And as you can notice from the welcome page, we are connected to the Nginx service that is running as part of our Nginx deployment within the Kubernetes cluster. Now I'll create another ingress resource for a different deployment. And let's see if our OCI Cloud Native Ingress Controller handles another ingress resource smoothly. I'll open up the manifest for another ingress resource that I have configured. In this manifest, we have defined the deployment definition for a test echo server that is running the image echo server 1.4. And we also have defined the service section that exposes our deployment on port 8080. And at the very bottom, we have the definition for our ingress resource. Under the rule sections, we have defined that this is the rule that applies to HTTP traffic, and the path specifies the path for which the rule applies. The path type is set to exact, where we are looking for an exact path match with the value test echo 1. And the backend service is defined where the name of the service is test echo 1, which we have already defined here. Port number here is defined as 80, indicating that the traffic should be forwarded to port 80 of the backend service test echo 1. I'll close this manifest and apply it on our Kubernetes cluster. I'll hit enter. Well, as you can notice, our deployment has been created. The service exposing the deployment is created, as well as the ingress resource has been created. Now let me run the kubectl get ingress command. From the output, we can see there are 2 ingress listed. The first one is from our previous deployment, which we already saw, and this one is from the current deployment where we deployed an echo server. And as you can notice, it is pointing to the same load balancer IP. And now to route the traffic to the test echo server deployment that we have created in our Kubernetes cluster, I need to specify the exact path as defined in the rules section. And it was /test echo 1. I'll go ahead and hit enter. And as you can notice, we have received some header values from our echo server pod that are running within our Kubernetes cluster. Now with this, it is clear that using OCI Cloud Native Ingress Controller, we are able to navigate to multiple backend services using just one load balancer IP. And all of this is made possible using the routing rules. And like I mentioned, you can add route rules to the ingress resource manifest. Here, the OCI native ingress controller supports host-based routing, path-based routing, both host and path-based routing, as well as default backend routing. When I say host-based routing, you can route requests based on host. You can add a host field under the rules field. And you can configure the OCI native ingress controller to route an incoming request based on the domain name in the request host header. As defined in the following example, we have a host value set to foo.bar.com, and with the help of this rule, all the requests sent to this domain name will be diverted to a backend service named Service A on service port 80. And like I mentioned, you can also route requests to different backend services based on path. For example, in this code snippet, as you can notice, there are multiple path types defined, and they both are following different rule to route request based on the path to which the request was originally sent. If the request starts with /app1, the OCI native ingress controller will route the request to the backend service with the name Service A on port 80. But if the request ends with the path /app2, it will be redirected to Service B running on port 443. You can also have a mix of host and path based routing, where you specify both the host field as well as multiple paths in your manifest file. And lastly, like I mentioned, you can route requests to a default backend. You can configure the OCI native ingress controller to route incoming requests to a default backend. And you might configure a default backend to handle requests that do not match any route rules. For example, you might define a default backend section within your ingress resource. As the definition here says, if none of the rules apply, your request will be routed to Service C on port 88. In addition, you can use annotations to customize the behavior of the OCI native ingress controller and the OCI load balancer. These are the list of annotations that you can customize to control the behavior of your OCI native ingress controller. There are different annotations to customize general behavior as well as annotations to customize health check behavior. You can define pod readiness gates, which are additional conditions included in a pod manifest to indicate that a pod is ready to receive traffic. Pod readiness gates enables you to implement complex custom readiness checks and can help you to achieve zero downtime during rolling deployments. All you need to do is specify that the OCI native ingress controller is to inject a pod readiness gate into the pod spec of every pod created in a particular namespace. You can run the command kubectl label ns, provide the namespace name, and provide the annotation which says pod readiness ingress oraclecloud.com /pod readiness gate inject is set to enabled. I'll go ahead and apply this in our Kubernetes cluster. I'll change the namespace placeholder with the default namespace. And hit enter. Well, the namespace default has been labeled and the pod readiness gate has been injected. Now I'll delete the deployment and services I created. Let me do it for the Nginx deployment, and then we will reapply it to our Kubernetes cluster and check the pod readiness gate. Alright, our Nginx deployment and its service has been deleted. Now I'll run the kubectl apply command and create the deployment again, and this time the pods will be labeled with the pod readiness gate annotation. I'll hit enter, and now I'll run the kubectl get pods -o wide with -w flag to watch the pod readiness gates. And as you can notice, the readiness gates column has the values 0 by 1, and after a while it has changed to 1 of 1, which means all the pods are ready to accept the traffic. I'll exit the command, and if I rerun the kubectl get pods command, this time without the watch flag, I'll clear the screen first and hit enter. We can confirm that the pod readiness gates have been applied to the Nginx deployment with the name Mahindra-deployment, And the readiness gates column specifies that all 3 pods are ready to accept the traffic. I hope you liked this video so far. See you in the next one. Thank you for watching. Welcome back to our final segment on exploring the OCI native ingress controller. Let's continue from where we left off in the previous video. Let's get started. You can also use the OCI native ingress controller to support secure HTTPS communication. Using the OCI native ingress controller, you can set up OCI load balancers, listeners, and backend sets to handle traffic encrypted using TLS, formerly known as SSL. And lastly, you can review ingress resource manifest validation errors detected by OCI native ingress controller through pod logs. To review the log of the pod running on the OCI native ingress controller, you can simply obtain the name of the OCI native ingress controller pod by entering the kubectl getPods command. To review the log of the pod running the OCI native ingress controller, we'll simply copy the command to get the pod names. I'll copy the command and paste it on my local machine. This returns me the pod names of all the OCI native ingress controller pods. Once you get the names of the pod running the OCI native ingress controller, and if multiple pod names are returned, we must identify the leader by reviewing the log for each pod, and we must eliminate the pods that are stuck in an acquiring lease state. We can simply run the command kubectl logs -f, provide the name of the pod, and provide the namespace, which is native ingress controller system. I'll copy this command and let's check which of our pod is running as a leader. I'll replace the pod name placeholder with the pod name. I'll go in the order of pod names listed. I'll copy the first pod name and paste it here. Hit enter. Well, from the output it's clear that this pod is not our leader pod because it's continuously looping at failed to acquire lease. I will kill this command and I'll clear the screen. I'll rerun the getPods command. And this time I'll specify the second pod name. I'll simply copy the pod ID and hit enter. Well, our second pod is also not the leader pod. I'll kill the command, clear the screen, rerun the kubectl getPods command. This time I'll provide the third pod name in the list. I'll just copy the pod ID and hit enter. Well, from the output we can see that most of the work is being done on this pod, which means this is our leader pod. And just in case you encounter any validation errors, you can simply search for validation failure string within the pod log and try to eliminate the error. Now let's take a look at some of the key points to note when using OCI native ingress controller. The Kubernetes cluster must be running Kubernetes version 1.25.4 or higher. The cluster must have load balancer subnet security rules configured, and this is very important. As you can read from the official documentation itself, the prerequisites mention that the load balancer security rules to allow inbound and outbound traffic to and from the load balancer subnet must be configured. And to view the ingress and egress rules, you can click on the given link. And here, just scroll down, notice all the ingress and egress rules that you must specify for your pod subnets, as well as the security rules for your load balancers and network load balancers. You must ensure to set up the ingress security rule in both your network security group which is recommended, or you can also set it in the security list associated with the load balancer. Moving on, the cluster can be using either the OCI VCN native pod networking CNI plugin or the Flannel CNI plugin for pod networking. There's a catch here. If the cluster uses the OCI VCN native pod networking CNI plugin for pod networking, the OCI native ingress controller will add pods as backends, as we had seen in the demonstration. And if the cluster uses the Flannel CNI plugin for pod networking, the OCI native ingress controller will add the worker nodes as backends. And one more thing to note is that the OCI native ingress controller only supports backend services of type node port as specified in the services manifest. The use of instance principals to enable the OCI native ingress controller to access OCI services and resources is not supported in clusters using virtual nodes. Another thing to note is you can specify workload identity principals only with enhanced clusters and not with basic clusters. With this, we come to the end of this lesson where we saw how to configure the OCI native ingress controller on your container engine for Kubernetes clusters. Hello and welcome to this lesson on running applications on ARM-based nodes. I am Mahendra Mehra, your senior OCI instructor at Oracle University. So let's get started. Compared to other shapes, ARM-based shapes provide better price performance, greater security isolation. Here, each core operates as a single threaded entity, improving the security of your applications and data, thus resulting in more consistent performance. Typically, developers use ARM-based worker nodes in Kubernetes cluster to develop and test applications. Selecting the right infrastructure is crucial for optimal performance, and when it comes to running applications on ARM-based nodes, you have a range of options at your fingertips. First up, consider the choice between ARM-based bare metal shapes and flexible VM shapes. Each comes with its own unique advantages. Now let's talk about the heart of it all, the Ampere A1 compute instances. These instances are driven by the cutting-edge Ampere Ultra processor, ensuring high performance and efficiency for your workloads. You must specify the ARM-based node pool shapes during cluster or node pool creation. Whether you choose to navigate through the user-friendly console, leverage the flexibility of the API, or command with precision through the CLI, the process remains seamless. Now let's explore the flexibility of defining pods to run exclusively on ARM-based nodes within a heterogeneous cluster setup. In scenarios where a cluster comprises node pools with ARM-based shapes alongside other shapes such as AMD 64, you can employ a powerful tool called Node Selector in the pod specification, as highlighted in the red font on the screen. This allows you to precisely dictate that an application should exclusively run on ARM-based worker nodes, ensuring your workloads aligns with the desired architecture. For instance, consider the following configuration file. It serves as a blueprint for defining a pod set to execute specifically on any ARM-based node within the cluster. The node selector field in the pod specification is where you define the requirements based on the node labels. It's a map of key value pairs that must match the labels of nodes for the pod to be scheduled on these nodes. In this example, the pod name nginx will only be deployed on those nodes who have the label as defined in the node selector field. If you want to deploy an application on both ARM-based and non-ARM-based worker nodes in the same cluster, you must use multi-architecture images, sometimes known as manifest list, which are stored in an open container initiative compliant registry like Oracle Cloud Infrastructure Registry. This is the example of manifest list, which contains multi-architecture images. As you can see, as you can notice, one of the images being used is Golang Alpine and the other one is Alpine latest. You build multi-architecture images from a single source tree with one image tag that include images for both x86 and ARM architectures. And you can build multi-architecture images using Docker BuildX, Podman, and tools like Builda. When working with ARM-based nodes in Kubernetes clusters, there are some essential considerations that ensure a seamless configuration experience. Firstly, note that you can specify ARM-based shapes for node pools in clusters running Kubernetes version 1.19.7 or later. Once you've created a node pool with an ARM-based shape, it's important to keep in mind that you cannot alter the node pool to have a non-ARM-based shape afterward. Similarly, if you have configured a node pool with a non-ARM-based shape, you cannot switch it to have an ARM-based shape. In addition, when specifying an ARM-based shape for a node pool, you must also choose an image that is compatible with the selected shape. This ensures that your configuration remains harmonious and optimized for the desired ARM-based environment. To recap, we've explored the benefits of ARM-based nodes, emphasizing better price performance and security. When configuring clusters, specify ARM-based shapes wisely and utilize node selectors to define pods for exclusive ARM-based execution. Armed with these insights, you are poised for optimal performance in your application deployments. I trust you found this video insightful. See you in the next one and thank you for tuning in. Hello and welcome to this demo on running applications on ARM-based nodes. In this demonstration, we are going to explore the deployment of an Nginx application on ARM-based nodes within our container engine for Kubernetes cluster. Let's walk through the process step by step. I'll transition to the OCI console. Well, I've already logged in into my OCI account and this is my OCI console. I'll go to the Kubernetes clusters service page. And this is the cluster on which we'll be performing the demonstration, which is OKE public demo 1. Let me duplicate this tab so that it becomes easier for us to navigate between the Cloud Shell machine. Let me also open up the Cloud Shell machine. Opening different tabs makes it convenient for us to switch between the manifest file and the Kubernetes cluster service page. All right, our Cloud Shell machine is up and running. I'll maximize this terminal. I'll clear the screen, and to clear the screen, the shortcut is Ctrl L. Firstly, we have a pod specification file that defines a simple Nginx container. I'll go to the Kubernetes example directory and open up the Nginx pod specification file. This is the pod specification for our Nginx pod. As you can see, the API version is v1, kind value is pod. Under metadata field, we have specified the name for our pod and the label with key value pair as environment test. The spec field contains information about our container, that is, we have given it a name Nginx. The image to be used is Nginx, and the image pull policy is if not present on the local machine. And pay attention to the node selector field, which is crucial for our demonstration. This field specifies that the pod should be scheduled on nodes with the label kubernetes.io/arc arm64. The Kubernetes scheduler will use this information to ensure proper placement of this pod. Let me close this file. I'll press Ctrl X. Now, before I apply this pod specification file on our Kubernetes cluster, which is OKE public demo 1, let's verify the current worker nodes in our OKE cluster. I'll click on the Kubernetes cluster here and scroll down under the node pools section. I'll click on pool 1 I'll scroll down here and under the nodes section, we have these 3 worker nodes, right? Now I'll open up these worker nodes on separate tabs. Let's check what are the shapes these worker nodes running on. I'll first select the first worker node. And from the instance information tab of this first worker node, I'll scroll down and under the shape configuration label, we can confirm that the shape being used by this worker node is VM standard E3 Flex, which is one of the AMD processor options. Let's check the shape of the remaining worker nodes. For worker node with label -1, I'll scroll down here and again the same shape, that is VM standard E3 Flex, is being used. And for worker node that ends with -2, and under the shape configuration details, we can verify that it is also using VM standard E3 Flex, which is an AMD processor type. And as observed, all the nodes in the existing node pool 1, are using AMD shapes, and none of them match the ARM based processor criteria. Now let's go back to our Cloud Shell terminal and just apply this pod specification file and see the output. I'll run this pod specification file using the kubectl apply command. I'll hit enter. And it says pod nginx created, but let's check the status of the pod. I'll run the kubectl get pods command. Well, from the output, it's evident that the kube scheduler was not able to locate a suitable node running ARM-based processor, and which is why the nginx pod went into pending status. I'll delete the pod now using kubectl delete pod command. And from the output, we can confirm that the pod nginx was deleted. Let's reconfirm that using kubectl get pod command. And no resources found in the default namespace. Now to address this, let's dynamically adapt our cluster and we'll add a new node pool. We will name it ARM pool, which is specifically designed with a worker node running on an ARM based shape. I'll navigate to the next tab where we have the Kubernetes cluster page open. I'll click on the cluster details from the breadcrumb menu. And here under the node pools in the resources section, I'll click on add node pool now to add a node pool. Let's name it ARM pool. And the compartment is ctd OKE where we are creating this node pool. The node type is manage nodes. Let the version be the latest version. Let's select an availability domain and the worker node subnet. Let's select a fault domain, although it's optional, but okay if I select one. And now in the shape and image section, let's select a node shape that belongs to ARM processor type. I'll select the VM standard A1 flex shape. I'll scroll down and let the image be Oracle Linux 8, which is compatible with ARM based shapes. And I'll change the node count to 1 over here. Under pod communication field, let's select the subnet for our pod communication, which is our node subnet. And I'll click on add to add this node pool to our OKE cluster. To check the progress of node pool creation, we'll click on work request. And as you can see, there's an entry for node pool create operation, which has been accepted. We'll need to wait until the node pool is created and attached to our OKE cluster, OKE public demo 1. Well, after a few minutes, my node pool create operation has succeeded. And let's check whether the node pool has been added to our cluster. I'll select the node pools from the resources section. And as you can see from the list, we have another node pool attached to our cluster with the name ARM pool having one worker node. I'll select this worker node over here. And from the shape label here, we can confirm that this worker instance or worker node is running using VM standard A1 Flex, which is an ARM-based processor variant. Now I'll scroll down to check the private IP address assigned to this worker node. It is 10.0.10.9. Now let's go back to our Cloud Shell terminal and run the kubectl get nodes command for this cluster. Originally we had one node pool with 3 worker nodes. Now we have added another node pool with 1 worker node to it. So overall we have 4 worker nodes running on this cluster. Well, there you go. The list specifies 4 worker nodes, and the last entry is for the one that we recently added using the ARM-based processor shape. Now I'll run the kubectl describe node command to check the labels associated with this worker node. I'll copy the node IP and paste it here. I'll hit enter. And let's scroll up to check the labels and ensure that there is a label that exists with kubernetes.io/arc ARM64. And there you go. Since this worker node is running on an ARM-based processor, Kubernetes has assigned it a label kubernetes.io/arc equals to ARM64. And this is the label we have defined in our node selectors in the pod specification file. I'll clear the screen now. Now I'll reapply the pod specification file and see if the kube scheduler can schedule it on the new worker node. I'll hit enter here. And the output says pod nginx created. Let's check the pod status. I'll hit enter. Notice how this time the nginx pod successfully deployed on a worker node with the IP address 10.0.10.9, which we specifically created using the ARM-based shape. This demonstrates the dynamic adaptability of our OKE cluster, allowing for precise scheduling based on node characteristics. It's a powerful feature for tailoring your infrastructure to match application requirements. I hope you enjoyed this demo and gained valuable insights. Stay tuned for more exciting content. See you in the next one. Thank you for watching. Hello and welcome to this lesson on running applications on GPU nodes. I am Mahendra Mehra, your senior OCI instructor at Oracle University. Let's get started. Originally designed for graphics manipulations, GPUs prove highly efficient in parallel data processing. This makes them a top choice for deploying data-intensive applications. NVIDIA GPUs, renowned for massive parallel computing, utilize CUDA libraries. Specific GPU models like NVIDIA Tesla Volta and Pascal require corresponding CUDA library versions for optimal performance. Let's explore the immense advantages of harnessing the parallel computing prowess of GPUs, making them the perfect choice for data-intensive applications. Our GPU nodes utilize cutting-edge NVIDIA graphics cards, ensuring efficient and powerful data processing. Seamless access to this computing prowess is made possible through CUDA libraries. To ensure smooth integration, be sure to select a GPU shape and opt for an Oracle Linux GPU image preloaded with the essential CUDA libraries. CUDA here is Compute Unified Device Architecture, which is a parallel computing platform and application programming interface model created by NVIDIA. It allows developers to use NVIDIA graphics processing units for general purpose processing rather than just rendering graphics. Let's explore some crucial factors when dealing with GPU nodes. First, note that GPU shapes are compatible with Kubernetes clusters from version 1.19.7 onward. When specifying the GPU image, make sure to choose the image having GPU in its name, whether through the console, API, or CLI. It's important to remember that once you make a choice between GPU and non-GPU, changes become irreversible. Keep in mind that the availability of GPU shapes may vary across different availability domains. For seamless use of GPU shapes, ensure the integration of the Kubernetes API into your VCN. Lastly, when running applications, opt for GPU worker nodes within managed node pools, as virtual node pools do not support GPU functionality. Now let's dive into defining a pod to specifically run on nodes equipped with GPUs. The configuration file here exemplifies defining a pod that is set to operate on any node within the cluster possessing at least one available GPU resource, regardless of the GPU type. This simple yet powerful configuration ensures your pod runs seamlessly on nodes with GPU resources, paving the way for GPU accelerated workloads. Let's explore the range of GPU shapes supported by Container Engine for Kubernetes. These shapes provide the foundations for GPU accelerated computing within your Kubernetes environment. For virtual machine GPU shapes, we have VM GPU 2.1, 3.1, 3.2, 3.4, and VM GPU A10.1, VM GPU A10.2. And for bare metal GPU shapes, we have VM GPU 2.2, 3.8, 4.8, and A100-V 2.8, and VM GPU A10.4. Please note that the availability may vary based on service limits and compartment quotas. Some shapes may not be accessible in your specific tenancy. To wrap up, we've navigated the GPU landscape, exploring its capabilities and the essential considerations in OKE. Armed with this knowledge, you are ready to elevate your applications with the power of GPU nodes. I hope you enjoyed watching this lesson. See you in the next one. Thank you for watching. Hello and welcome to this demo on running applications on GPU nodes. I am Mahendra Mehra, your senior OCIR instructor at Oracle University. Let's dive in. In this demo, we'll delve into deploying applications on GPU nodes within Container Engine for Kubernetes cluster. Let me go to the Kubernetes cluster page. We will be running our demo on the cluster titled OKE Public Demo 1. I'll click on this cluster and go to the cluster details page. On a separate tab, I've opened up the Cloud Shell machine already, and I'm currently in my Kubernetes examples directory. Let's start by examining the pod specification file, which we'll be deploying on our Kubernetes cluster. Now let me explain the specifications. The pod is named CUDA GPU workload with a restart policy set on failure. It runs a container named CUDA vector add and pulls the image from this location. More importantly, it specifies resource limits, specifically one NVIDIA GPU resource. I'll exit this file using Ctrl X. Moving to our previous tab, our OKE cluster, OKE Public Demo 1. This cluster consists of two node pools. Let me scroll down and go to the node pools section. Pool 1 has total of 3 worker nodes. I'll bring them up. And all 3 worker nodes are running on VM standard E3 Flex shape, which is AMD processor shape type. And the second node pool in the list, which is ARM pool, is running on one worker node using the shape VM standard A1 Flex. This is an ARM processor based shape, which means none of these pools are running on shapes having support for GPU resources. Now let's apply the pod spec to our cluster and see the output. I'll hit enter here. It says pod CUDA GPU workload created, but let's check the pod status. And as you can notice, pod CUDA GPU workload is in pending status, as the Kubernetes scheduler can't find a suitable worker node meeting the GPU requirements set in the pod specification file. Now to address this, we'll create a new node pool and add a worker node with a GPU based shape. I'll navigate to the first tab, and here let's go to the node pool section. I'll click on the cluster details link from the breadcrumb. Let's scroll down and click on node pools. I'll click on add node pool and let's give it a suitable name. Well, the compartment in which I'm creating this node pool is ctd-oke and the node type is managed. I'll leave the version as the default version. Under node placement configuration, I'll select one of the availability domain and select the worker node subnet. I'll leave the default domain as optional. I'll add another row and select another availability domain, as the GPU shapes are not necessarily available in every availability domain. So I'm expanding my options. I'll select the AD2 availability domain and select the worker node subnet. Leave the default domains blank and add another row. Add the third availability domain. Select our worker node subnet and leave default domains blank. Now under the shape and image section for the node shape, I'll select the GPU based processor shape. I'll go ahead with VM GPU A10.1 shape. And it has automatically fetched an image that is compatible to the VM GPU A10.1 node shape, which is Oracle Linux 8, and the build is Gen 2 GPU. Under the node pool options, I'll reduce the node count to 1. And for the pod communication field, I'll select the worker node subnet. Now I'll click on add. Well, it says the selected shape is not supported in the availability domain AD2. Let me remove this entry. And let's click on add button. Well, it will take some time before our new node pool GPU pool gets added to the list of node pools. Well, we have an entry for our new node pool that we just created, that is GPU pool, but the node pool status says it's still in the creating state. Let's wait until it turns active. Alright, after a while, our GPU pool, which is a managed node pool, is now active. I'll click on the pool to get the worker node detail. And as you can notice, the worker node in the GPU pool is running using node shape VM GPU A10.1, which is a GPU based processor. And it has a private IP address assigned to it, that is 10.0.10.253. Let's navigate to our Cloud Shell terminal and check the nodes status for our Kubernetes cluster using the kubectl get nodes command. Well, the list says that we have 5 worker nodes present in our cluster. And you can observe that we have the entry for our latest addition of worker node to our Kubernetes cluster that has the node name as 10.0.10.253. I'll clear the screen first. Now that we have a GPU based worker node in our node pool, let me check the pod status. I'll run the kubectl get pods -o wide command. Let me hit enter. Notice how the CUDA GPU workload pod has completed its execution and it was assigned to our worker node 10.0.10.253, which basically is our GPU based worker node. That's it from this demo. I trust you found this demo useful. See you in the next one. Thank you for watching. Welcome to this module of our course where we'll delve into configuring storage solutions for Kubernetes clusters within OCI Container Engine for Kubernetes. In this module, we'll take a look at the importance of configuring storage solutions and discuss various methods to achieve this within OCI. You'll learn how to provision persistent volume claims using the block volume service, enabling persistent storage for Kubernetes applications. Additionally, you'll understand the process of expanding block volumes to accommodate increased storage needs, while also investigate tweaking block volume performance to optimize storage performance according to your requirements. Furthermore, we'll explore different file system types available for block volumes and learn how to specify them. We will also cover provisioning persistent volume claims using the OCI file storage service, facilitating shared file storage for Kubernetes applications. Additionally, we'll delve into understanding the process of provisioning PVCs on both new and existing file systems. Let's dive into the world of Kubernetes storage solutions on OCI.